tonight I want to take you somewhere extraordinary, somewhere at the very edge of what we understand about reality itself. We're going to explore a place where two of the universe's most fundamental forces meet in ways that shouldn't be possible, where light itself behaves in ways that defy everything we thought we knew. Tonight, we're going to discover together what happens when light, that eternal wanderer of the cosmos, encounters the ultimate stillness of absolute zero. Before we begin this journey into the coldest corners of physics, I'm curious about where you are right now. Are you tucked into bed in a bustling city where lights twinkle outside your window, or perhaps you're in a quiet countryside where the stars shine undimmed by artificial glow? Whatever corner of our planet you're listening from, and whatever time shows on your clock as you settle in for this cosmic exploration, I invite you to make yourself comfortable. If you find these gentle journeys into the mysteries of our universe help you drift into peaceful sleep while feeding your curiosity, perhaps you'd like to subscribe for more of these nighttime wanderings through physics and space. Consider it your invitation to regular appointments with wonder, delivered in the quiet hours when the mind is most open to contemplating the impossible. It's a question that might sound strange at first, something you could easily dismiss as just another quirk of extreme physics. After all, light and cold seem to belong to entirely different realms of experience. Light brings warmth, energy, motion. Cold brings stillness, silence, the slowing down of everything. But the more we look at what happens when these two extremes meet, the more quietly intriguing it becomes. What if this bizarre encounter between light and absolute zero was not just a laboratory curiosity, but a quiet doorway into understanding how the universe really works at its most fundamental level? Let me paint you a picture of the cosmos we inhabit. This vast expanse where light has been traveling since the first moments after the Big Bang. Right now, as you listen to these words, photons that began their journey billions of years ago are just arriving at Earth, carrying messages from galaxies so distant that they might no longer exist. Light fills every corner of space, even the emptiest voids between galaxies shimmer with ancient photons, cosmic microwave background radiation that has been cooling and stretching for nearly 14 billion years. We live in an ocean of light, most of it invisible to our eyes, washing over us constantly in waves of radio, infrared, ultraviolet, X-rays, gamma rays, an endless spectrum of electromagnetic poetry written in frequencies we can barely imagine. And yet, for all its omnipresence, light remains one of the deepest mysteries in physics. It behaves as both a wave and a particle. It travels at a speed that nothing with mass can ever reach. It bends around massive objects and carries information across the universe instantaneously in its own reference frame. Every photon that has ever existed is, from its own perspective, born and absorbed in the same eternal instant, experiencing no time at all during its journey, whether it travels a millimeter or a billion light years. This is the paradox of light, that it defines time for the rest of us while existing outside of time itself. Now consider the other extreme of our story tonight, absolute zero, that theoretical point where all molecular motion ceases, where even the jittering of atoms comes to a complete stop. It's a temperature so cold that we measure it not in degrees but in fractions above it, because nothing in the universe can actually reach it completely. Absolute zero sits at negative 273.15 degrees Celsius, or 0 Kelvin, named after Lord Kelvin, who first calculated this ultimate limit of cold. It represents not just the absence of heat, but the absence of the very possibility of extracting any more energy from matter. In our everyday experience, cold is simply less heat, less motion, less energy. When you touch an ice cube, you're feeling heat flowing from your hand into the ice, not cold flowing into you. But absolute zero is different. It's not just very cold, it's the complete cessation of thermal motion, a state so extreme that the normal rules of matter begin to break down. As we approach absolute zero, strange things happen. Gases become liquids, liquids become solids, and some materials become superconductors, carrying electricity with absolutely no resistance. Others become superfluids, flowing without any friction at all, capable of climbing up the walls of their containers and escaping, defying gravity itself in their perfect, frictionless flow. The universe itself has regions that approach these extreme temperatures. In the vast spaces between galaxies, where starlight barely reaches and matter is spread so thin that a volume the size of Earth might contain only a few atoms, temperatures can drop to just a few degrees above absolute zero. The Boomerang Nebula, 5,000 light-years away in the constellation Centaurus, is the coldest naturally occurring place we've discovered, with temperatures of just 1 degree Kelvin, colder even than the background temperature of space itself. It achieved this by expanding rapidly, its gases spreading and cooling in a cosmic demonstration of the same principle that makes the gas in your refrigerator cold. But even these cosmic refrigerators pale in comparison to what humans have achieved in laboratories. Using lasers, magnetic fields, and techniques that would seem like magic to scientists from just a century ago, we've cooled atoms to within billionths of a degree of absolute zero. In these extreme conditions, matter enters exotic states that don't exist anywhere else in the universe, at least not that we know of. Bose-Einstein condensates form, where thousands of atoms begin to behave as a single quantum entity, their individual identities merging into one collective quantum state. It's as if the atoms forget they are separate things and become one unified quantum organism, pulsing with synchronized probability waves. So what happens when light, that eternal traveler, encounters matter in these extreme states? What we've discovered challenges everything our intuitions tell us about how light should behave. The story begins in 1999, when physicist Lena Howe and her team at Harvard University conducted an experiment that seemed to violate one of the most fundamental constants in physics. They shot a pulse of light into a cloud of sodium atoms cooled to within billionths of a degree of absolute zero, forming a Bose-Einstein condensate. What happened next was extraordinary. The light, which normally travels at 290,358 meters per second in a vacuum, slowed down. Not just a little, but dramatically. It crept through the condensate at just 17 meters per second, about the speed of a car driving through a parking lot. Think about that for a moment. Light, which can circle the Earth 7.5 times in a single second, was moving slower than you could throw a baseball. The pulse of light that entered the condensate was like a cosmic speed demon suddenly forced to crawl through thick honey, except the honey was made of quantum probability itself. But this was just the beginning. As Howe and her team continued their experiments, they found they could slow light even further. By adjusting the properties of their condensate and the control lasers they used to manipulate it, they eventually slowed light to less than 1 meter per second, slower than a leisurely walk. The mechanism behind this seemingly impossible phenomenon lies in the quantum nature of the interaction between light and matter at these extreme temperatures. When photons enter the Bose-Einstein condensate, they don't simply pass through like light through glass. Instead, they become entangled with the quantum state of the atoms themselves. The photons are absorbed and re-emitted countless times, but in a coherent, coordinated way that preserves the information carried by the light pulse. It's as if the light temporarily becomes part of the condensate itself, adopting its languid, ultra-cold personality before eventually emerging on the other side. But the surprises didn't stop there. In 2001, Howe's team achieved something even more remarkable. They stopped light completely. They brought a pulse of light to a complete halt inside their condensate, held it there for a brief moment, and then released it to continue on its way. The light pulse emerged intact, carrying all the same information it had when it entered, as if it had simply paused its journey through space and time. For that fraction of a second, they had captured light, itself, holding it prisoner in a cage made of ultra-cold atoms and quantum probability. To understand how remarkable this is, we need to delve deeper into what light actually is and why it normally can't be stopped. A photon, a particle of light, has no mass. This means it must always travel at the speed of light in whatever medium it's passing through. It can't slow down in the conventional sense because it has no rest frame, no perspective from which it could ever be still. From a photon's point of view, its entire journey from creation to absorption happens instantaneously, whether that journey spans a millimeter or billions of light years. So how can we reconcile this with light being stopped in a Bose-Einstein condensate? The answer lies in understanding that what we're really doing is transferring the quantum state of the light into the atoms of the condensate. The photons are absorbed, but their quantum information, their phase, amplitude, and other properties are imprinted onto the collective quantum state of the condensate. The condensate holds this information like a quantum memory, preserving it perfectly because at these temperatures, there's virtually no thermal noise to disturb it. When we release the light, we're really creating new photons that carry the exact same quantum information as the originals. It's like the ultimate cosmic magic trick, making light disappear and reappear while preserving its essential nature. This process is called electromagnetic-induced transparency, or EIT, and it relies on the precise manipulation of quantum states using multiple laser beams. One laser, called the coupling laser, creates a quantum interference effect that makes the normally opaque condensate transparent to a specific frequency of light. The signal pulse, the light we want to slow or stop, can then enter the condensate. By gradually reducing the intensity of the coupling laser, we can transfer more and more of the light's energy into the atoms, slowing it down. Turn off the coupling laser completely, and the light stops, its quantum state fully transferred to the atoms. Turn the coupling laser back on, and the light re-emerges, continuing its journey as if nothing had happened. The implications of this discovery ripple outward through multiple fields of physics and technology. At the most fundamental level, it demonstrates the profound unity between light and matter at the quantum scale. The distinction between photons and atoms, between energy and matter, becomes blurry in these extreme conditions. They can exchange properties, share quantum states, and exist in hybrid forms that have no classical analog. It's a glimpse into the quantum foundations of reality, where the categories we use to organize our everyday experience break down into something more fluid and interconnected. Consider what this means for our understanding of information itself. A pulse of light can carry vast amounts of information, encoded in its amplitude, phase, frequency, and polarization. When we stop light in a Bose-Einstein condensate, we're storing this information in the quantum states of atoms. The condensate becomes a kind of quantum hard drive, capable of storing and retrieving optical information with perfect fidelity. Unlike conventional data storage, which relies on magnetic or electronic states that can be corrupted by noise and interference, this quantum storage is protected by the fundamental laws of quantum mechanics. This has profound implications for the development of quantum computers and quantum communication networks. One of the biggest challenges in quantum computing is maintaining quantum coherence, keeping quantum states from decohering due to interaction with the environment. Bose-Einstein condensates, with their extreme cold and collective quantum behavior, provide an almost perfect environment for preserving quantum information. Light stopped in a condensate could serve as a quantum memory, storing quantum bits or qubits for quantum calculations. Even more intriguingly, this phenomenon could enable the creation of quantum repeaters for long-distance quantum communication. One of the limitations of sending quantum information through optical fibers is that the signal degrades over distance, and unlike classical signals, quantum signals can't be simply amplified without destroying their quantum properties. But if we could stop light at regular intervals, store its quantum state, and then regenerate it, we could extend the range of quantum communication indefinitely. Imagine a future quantum internet where information travels as pulses of light, pausing at ultra-cold way stations to rest before continuing their journey. The story becomes even stranger when we consider what happens to time itself in these experiments. From our external perspective, the light pulse spends a measurable amount of time stopped in the condensate. We can time it with our clocks, observe it with our instruments. But from the perspective of the light itself, if photons could have a perspective, what happens during this pause? Does time stop for the light? Does it experience the interval as an instant or an eternity? These questions touch on some of the deepest mysteries in physics, the nature of time, the relationship between quantum mechanics and relativity, the role of observation in defining reality. As we've pushed these experiments further, we've discovered even more exotic behaviors. Scientists have found ways to slow light in materials other than Bose-Einstein condensates, using everything from ruby crystals to photonic crystals to specially designed metamaterials. Each approach reveals new facets of how light and matter interact at the quantum level. In some cases, they've achieved what's called negative group velocity, where the peak of a light pulse appears to exit a material before it enters, seeming to travel backward in time. Of course, no, information actually travels faster than light or backward in time, but the mathematics of wave propagation can create these counterintuitive effects. In recent years, researchers have gone beyond simply stopping light to actually crystallizing it. By arranging atoms in precise patterns and cooling them to near absolute zero, They've created conditions where photons behave like a solid crystal, with photons hopping from atom to atom in regular, predictable patterns. This state of matter, called a photonic crystal, or sometimes a light crystal, has properties unlike anything in our everyday experience. It's solid light, if you will, though not solid in any conventional sense. The photons maintain their fundamental nature as massless particles, but their collective behavior mimics that of electrons in a solid material. These light crystals could revolutionize how we process and transmit information. Unlike electronic circuits, which generate heat and have fundamental speed limitations, photonic circuits could operate at the speed of light with virtually no energy loss. The ability to control light at the quantum level, to stop it, store it, and release it on command, opens up possibilities for optical computing that could far surpass the capabilities of current electronic systems. Imagine computers that process information not with electrons flowing through silicon, but with light pulses dancing through ultra-cold quantum crystals. The journey of understanding what light does at absolute zero has also led us to question some of our most basic assumptions about the nature of light itself. We've long known that light exerts pressure, that photons carry momentum despite having no mass. But in Bose-Einstein condensates, we've observed light behaving in ways that suggest it can have properties we never imagined. Under certain conditions, photons can form bound states, sticking together like molecules. These photonic molecules behave as single entities, their constituent photons correlated in ways that classical physics says should be impossible. This binding of photons has been achieved by firing laser light through clouds of ultra-cold atoms, where the interaction between the photons is mediated by the atoms. The photons don't directly interact with each other, they have no electric charge and normally pass right through each other. But in the presence of the ultra-cold atoms, they can become correlated, their quantum states entangled in ways that make them behave as if they were attracting each other. It's a kind of artificial interaction, mediated by matter, but the result is genuine bound states of light. These photonic molecules could be the building blocks for entirely new forms of technology. If we can make photons interact strongly with each other, we can create optical transistors, switches, and logic gates that operate with single photons. This would enable quantum computers that use light instead of matter to store and process quantum information. The advantages would be enormous. Light is naturally resistant to many forms of decoherence. It can travel long distances without degradation, and it can be easily interfaced with existing optical communication infrastructure. As we explore deeper into this realm where light meets absolute zero, we're also discovering new fundamental physics. The interaction between light and ultra-cold matter is teaching us about phase transitions, those moments when matter changes from one state to another. But these aren't the familiar phase transitions of water freezing into ice or boiling into steam. These are quantum phase transitions, where the change is driven not by temperature but by quantum fluctuations. A Bose-Einstein condensate can transition from a superfluid state to an insulating state, from a phase where atoms flow without resistance to one where they're locked in place, and light can trigger these transitions. The control we now have over light at these extreme temperatures is almost magical in its precision. Scientists can sculpt light pulses into any shape they want, compress them or stretch them, split them or combine them, all while preserving their quantum properties. They can create dark pulses, regions where light is absent, that propagate through the condensate like holes in the light field. These dark pulses behave like particles themselves, with their own dynamics and interactions. It's a photographic negative of normal light propagation, shadows that travel and interact like substantial things. One of the most beautiful phenomena observed in these systems is called slow light solitons. A soliton is a wave that maintains its shape as it travels, neither spreading out nor breaking up. In normal materials, light pulses spread out as they propagate, because different frequencies travel at slightly different speeds. But in Bose-Einstein condensates, under just the right conditions, light pulses can form solitons that travel slowly, but maintain their shape perfectly. These solitons can collide with each other and emerge unchanged, passing through each other like ghosts. They represent a perfect balance between dispersion, which tends to spread the pulse out, and nonlinearity, which tends to focus it. The study of light at absolute zero has also revealed surprising connections to other areas of physics. The mathematics that describes slow light in Bose-Einstein condensates is remarkably similar to the mathematics of black holes and event horizons. When light slows down in a condensate, it creates an effective event horizon for other excitations in the system. Just as light cannot escape from inside a black hole's event horizon, certain excitations in the condensate cannot escape from regions where light has been slowed or stopped. This has led to proposals for creating dumb holes, acoustic analogues of black holes, in ultra-cold atomic systems, where sound plays the role that light plays in real black holes. These connections between seemingly unrelated areas of physics hint at deep underlying unities in nature. The same mathematics appears in different guises throughout physics, from the behavior of light in ultra-cold atoms to the dynamics of the early universe. By studying light at absolute zero, we're not just learning about a curious laboratory phenomenon, we're uncovering fundamental principles that apply across scales from the quantum to the cosmic. As we continue to push the boundaries of what's possible with light and ultra-cold matter, new surprises keep emerging. Scientists have recently discovered that they can use stopped light to create quantum memories that can store not just single pulses but entire images. By stopping a light field that contains spatial information, an image, they can store that image in the quantum states of the atoms and retrieve it later. The image is stored not as pixels or points, but as a quantum hologram, a three-dimensional pattern of quantum correlations. This could lead to quantum holographic memories with storage densities far exceeding anything possible with classical technology. The interaction between light and absolute zero is also teaching us about the nature of the vacuum itself. Even in the emptiest space, quantum fluctuations create virtual particles that pop into existence and disappear again. These vacuum fluctuations can be modified by the presence of ultra-cold matter, creating regions where the vacuum itself has different properties. Light traveling through these modified vacuums can experience forces and accelerations that wouldn't exist in normal space. It's as if the ultra-cold matter rewrites the rules of empty space in its vicinity. Perhaps most remarkably, these experiments are bringing us closer to understanding the quantum nature of space-time itself. In some theories of quantum gravity, space-time at the smallest scales is not smooth but granular, made up of discrete units like pixels on a screen. The behavior of light in ultra-cold matter might provide a way to test these theories. If space-time is granular, light traveling through it should experience tiny delays that accumulate over cosmic distances. By studying how light propagates through artificial spacetimes created in ultra-cold atoms, we might gain insights into the structure of real spacetime. The practical applications of stopped and slow light continue to multiply as our understanding deepens. Quantum radar systems could use the quantum correlations preserved in stopped light to detect stealth aircraft that are invisible to conventional radar. Quantum sensors could use the extreme sensitivity of light-matter interactions at ultra-cold temperatures to detect gravitational waves, dark matter, or other elusive phenomena. Quantum batteries could store energy in the form of stopped light, releasing it on demand with perfect efficiency. In medicine, the ability to control light at the quantum level could enable new imaging techniques that can see through opaque tissue without damaging it. By using quantum correlations preserved in slow light, it might be possible to reconstruct three-dimensional images of the inside of the body with resolution far exceeding current methods. The quantum nature of the light would allow it to extract information that classical light cannot access. The story of light at absolute zero is also a story about the boundaries of our knowledge and the surprises that await us at those boundaries. Every time we push into a new regime of physics, whether it's the very fast, the very small, the very massive, or in this case, the very cold, we discover that nature has more tricks up her sleeve than we imagined. The universe is not just stranger than we imagine, as the saying goes, but stranger than we can imagine. As we lie here tonight contemplating these wonders, it's worth reflecting on how far we've come in our understanding of light. From the ancient Greeks who thought vision worked by rays emanating from our eyes, to Newton who imagined light as particles, to Maxwell who showed it was electromagnetic waves, to Einstein who revealed its quantum nature, each generation has peeled back another layer of the mystery. And now, in laboratories cooled to temperatures colder than anywhere in the natural universe, we're discovering that light still has secrets to reveal. The photons streaming from your bedside lamp or phone screen right now are cousins to the photons that scientists trap in their ultra-cold prisons. They obey the same fundamental laws, carry the same quantum mysteries. The difference is only in the environment they encounter. In the warmth of your room, they zip along at their accustomed speed, barely interacting with the matter they pass through. But if we could cool your room to within a whisper of absolute zero, those same photons would slow to a crawl, their quantum nature revealed in all its strange glory. This duality, the familiar and the exotic existing within the same phenomenon, is one of the most beautiful aspects of physics. The same light that warms your face on a sunny day can be stopped in its tracks by a cloud of ultra-cold atoms. The same quantum mechanics that governs the unfathomable coldness of a Bose-Einstein condensate also governs the chemistry of your body, the electronics in your devices, the fusion in the stars. We live in a quantum universe, but most of the time, the quantum nature is hidden by thermal noise, averaged out by the countless interactions happening every second. At absolute zero, or as close as we can get to it, that thermal veil is lifted. The quantum world reveals itself in its pure form, unmasked and undisguised. And what we see there is both alien and fundamental, a world where our everyday intuitions fail, but where the mathematical beauty of physical law shines through with crystalline clarity. Light stopping and starting, forming, molecules and crystals carrying information through quantum correlation rather than classical propagation. These phenomena show us that our universe is far more flexible and strange than our everyday experience suggests. As research continues, new questions emerge faster than we can answer them. Can we create stable three-dimensional structures out of stopped light, optical crystals that could form the basis for entirely new technologies? Can we use the interaction between light and ultra-cold matter to simulate other physical systems, creating tabletop versions of cosmic phenomena? Can we push these techniques to even more extreme conditions, perhaps approaching the Planck scale, where quantum mechanics and gravity meet? Some theorists speculate that the ability to stop and store light might have implications for our understanding of time itself. If we can pause light, which in its own reference frame experiences no time, what does this say about the nature of temporal flow? Could advanced civilizations use stopped light to create temporal bubbles, regions where time flows differently? These are wild speculations, far beyond our current technology, but they emerge naturally from thinking about what we've already achieved. The interaction between light and absolute zero also raises philosophical questions about the nature of information and reality. When light is stopped in a condensate, its information is transferred to the atoms, but is it the same light that emerges when we release it? If every property is preserved, every quantum number and correlation, does it matter that the original photons were absorbed and new ones created? This touches on ancient philosophical questions about identity and continuity, but with a quantum twist. As we drift deeper into the night, consider the cosmic perspective on what we've discussed. Somewhere in the universe there might be natural phenomena that recreate these extreme conditions. In the accretion disks around black holes, where matter is compressed and heated to billions of degrees, there might also be regions where quantum effects create pockets of extreme cold. In the collisions between neutron stars where matter exists in states we can barely imagine, light might naturally slow and stop in ways we're only beginning to explore in our laboratories. The universe is full of extreme environments we've never observed directly. In the cores of planets made of metallic hydrogen, in the quantum seas of quark-gluon plasma that existed in the first microseconds after the Big Bang, in the hypothetical dark matter halos that surround galaxies, conditions might exist where light behaves in ways that would seem impossible to us. Our experiments with light at absolute zero might be revealing behaviors that are common elsewhere in the universe, but hidden from our telescopes. Even in the far future of the universe, as the stars burn out and cosmic expansion accelerates, the universe itself will approach absolute zero. In that distant epoch, trillions of years from now, will the last photons of light slow and stop, trapped in pockets of ultra-cold matter? Will the universe end not in fire or ice, but in slow light, creeping through a cosmos too cold to sustain the rapid propagation we take for granted? These are the kinds of questions that emerge when we push the boundaries of what's possible, when we create conditions in our laboratories that probe the limits of physical law. Each answer we find opens up new questions, new mysteries to explore. The discovery that light can be stopped at absolute zero is not an ending but a beginning, a doorway into new realms of physics we're only beginning to map. As you continue to rest tonight, perhaps you can imagine yourself as a photon, traveling across the cosmos at the ultimate speed limit, experiencing the universe in a single eternal moment. But then you encounter a cloud of ultra-cold atoms and suddenly, for the first time in your existence, you slow down. Time, which meant nothing to you before, suddenly becomes real. You find yourself suspended in a quantum limbo, neither fully light nor fully matter, waiting in the cold darkness for the signal that will release you to continue your journey. This is the strange borderland we've explored tonight, the place where light meets absolute zero, where the most energetic and the most still aspects of our universe come together in ways that challenge everything we thought we knew. It's a reminder that nature always has surprises in store for us, that the universe is not just vast in space but deep in possibility, filled with phenomena we've only begun to discover. The gentle hum of technology around you, the soft light of your screen or lamp, these everyday manifestations of electromagnetic physics contain within them the seeds of these exotic phenomena. The same physics that powers your daily life also enables the stopping of light, the creation of photonic molecules, the storage of quantum information in ultra-cold atoms. We live surrounded by potential wonders, waiting for the right conditions to reveal themselves. As sleep begins to approach, let your mind wander through these quantum realms we've explored. Picture the slow dance of photons through ultra-cold matter. They're usually frenetic energy transformed into a gentle waltz. Imagine the crystalline structures of stopped light, holding information in perfect quantum suspension. Think of the scientists working through the night in laboratories around the world, cooling atoms to temperatures that shouldn't exist, revealing new facets of light's nature with each experiment. The universe continues its work as you rest. Photons stream from distant stars, carrying their messages across the void. Some of them, perhaps, encounter natural conditions that slow them down, though we haven't discovered these cosmic laboratories yet. Others race onward at the speed of light, defining the very structure of causality in our universe. And in a few special places, in chambers cooled to near absolute zero, light pauses in its eternal journey, demonstrating once again that the universe is far more mysterious and beautiful than we ever dared to imagine. Tomorrow you'll wake to a world illuminated by ordinary light, moving at ordinary speeds, behaving in ordinary ways. But perhaps you'll remember this journey we've taken together, this exploration of a light's behavior at the ultimate extreme of cold. Perhaps you'll look at the morning sunlight differently, knowing that under the right conditions those racing photons could be brought to a complete stop, held in quantum suspension, then released to continue their journey as if nothing had happened. The mystery of light at absolute zero is really a mystery about the nature of reality itself. It shows us that the familiar world we experience is just one face of a much deeper and stranger universe. In the quantum realm, at temperatures approaching absolute zero, the ordinary rules break down and new ones emerge. Light can stop, photons can bind together, information can be stored in atomic clouds, and time itself becomes negotiable. These discoveries remind us that we're still in the early chapters of understanding our universe. Each new revelation, each impossible phenomenon made real in the laboratory, adds another piece to the vast puzzle of existence. We've learned that light can be stopped, but we're only beginning to understand what this means, what it implies for our theories of physics, what technologies it might enable, what other secrets it might help us unlock. As your consciousness begins to fade into sleep, carried on the gentle rhythm of your breathing, remember that you are part of this grand exploration. Every human who has ever wondered about the nature of light, from the first person who noticed their shadow to the scientists stopping photons in ultra-cold traps, has contributed to our collective understanding. We are the universe coming to know itself, using the very phenomena we study, light, matter, energy, to probe the mysteries of existence. In the quantum realm, where light meets absolute zero, we find not just exotic physics, but a reflection of the deep unity that underlies all of nature. The same laws that govern the cosmos govern the atoms in your body. The same quantum mechanics that allows light to stop in a Bose-Einstein condensate orchestrates the chemistry of life. We are not separate from these mysteries, but woven from the same quantum fabric, participants in the same cosmic dance. So as you drift into sleep, know that you rest in a universe of infinite wonder, where light can be stopped and started, where matter can exist in states that defy classical description, where the impossible becomes possible when we push the boundaries of what we know. The photons that reached your eyes today, carrying images of the world around, you are capable of feats that would seem like magic if we didn't have the mathematics to describe them. Let the mystery of stopped light be your gentle companion as sleep approaches. Like those photons suspended in ultra-cold atoms, you too can pause in your journey, resting in the quantum embrace of the universe. And when morning comes, like light released from its quantum prison, you'll continue on your path, carrying with you the knowledge that reality is far stranger and more beautiful than it appears. The universe doesn't require our understanding to continue its work, but it seems to reward our curiosity with ever deeper mysteries. Today we can stop light. Tomorrow we might learn to weave it into new forms of matter, to use it as the thread that connects quantum computers across the globe, to store information in its quantum correlations for millennia. Each discovery opens new possibilities, new questions, new frontiers to explore. In the silence of your room, as your breathing slows and deepens, you're surrounded by electromagnetic fields, by photons streaming from every surface, by the quantum vacuum fluctuating with virtual particles. This invisible ocean of light and possibility envelops you, connects you to the cosmos, makes you part of the same story we've explored tonight. You're made of star stuff, as Carl Sagan said, but you're also made of light stuff, quantum stuff, the same fundamental phenomena that we've learned to slow and stop in our laboratories. As the boundaries between waking and sleeping begin to blur, like the boundaries between light and matter in a Bose-Einstein condensate, let yourself drift into that quantum realm where normal rules don't apply. In dreams, as in quantum mechanics, impossible things happen routinely. Time flows backward, information travels instantly, and the observer and the observed become one. Perhaps dreams are our nightly journey into a quantum state of consciousness, where we experience the universe more as it truly is, uncertain, probabilistic, full of superposition and entanglement. The story of light at absolute zero will continue tomorrow, next year, next decade. Scientists will push to even lower temperatures, find new ways to manipulate light, discover new quantum states of matter and energy. Each generation will add new chapters to this story, revealing aspects of nature we can't yet imagine. But tonight, in this moment, you've been part of that story, a conscious observer contemplating the mysteries of light and cold, of quantum mechanics and cosmic possibility. Sleep now, carried by the same physical laws that allow light to stop and start, that govern the dance of atoms at absolute zero, that write the equations of reality in a language we're still learning to read. Rest in the knowledge that you live in a universe of boundless mystery and beauty, where even light itself can pause to rest before continuing its eternal journey. And as you drift into sleep, you remain part of this quiet universe, wrapped in its laws, carried by its mysteries, gently, peacefully, into the night where photons dance slowly through your dreams, where absolute zero whispers its secrets, where the impossible becomes possible in the quantum realm of sleep and stars. End.